Welcome! In this session, we will explore problem number 1023, Camelcase matching. This problem requires us to determine whether each string in a list of queries matches a given pattern based on Camelcase rules. We'll break it down step by step and discuss an efficient approach to solve it. Let's dive in. In this problem, we are given two inputs, a list of strings called queries and another string called pattern. The goal is to determine which strings in the queries list match the pattern. A query is considered a match if we can insert some lowercase English letters, possibly none, at arbitrary positions in the pattern such that the uppercase letters in the pattern remain in the same order and align with the uppercase letters in the query. The output is a Boolean array called result, where each element indicates whether the corresponding query matches the pattern. For the input format, queries can contain up to 1,000 strings, and each string can have a length of up to 100. The pattern string also has a maximum length of 100. The output is a Boolean array of the same length as queries, where each value is either true or false depending on the match result. Let's look at the first example to clarify this further. Here, queries is given as foobar, foobar test, football, frame buffer, force feedback, and the pattern is FB. The output is true, false, true, true, false. For each query in queries, we check if it matches the pattern. For instance, foobar matches FB because we can insert lowercase letters between and around the uppercase letters F and B to form foobar. However, foobar test does not match because it contains uppercase letters beyond what is present in the pattern. Similarly, football matches FB, and so does frame buffer. But force feedback does not match because it has extra uppercase letters after matching FB. This example demonstrates how the order of uppercase letters and the presence of extra uppercase letters impact the result. Now, in the second example, queries is competitive programming, counterpick, control panel, and the pattern is coop. The output is false, false, true. For competitive programming, the match fails because the uppercase letters do not follow the order specified in the pattern. Likewise, counterpick fails for the same reason. However, control panel matches because the uppercase letters align perfectly with the pattern, and the lowercase letters can be inserted as needed to complete the match. This shows how both the order and alignment of uppercase letters play a critical role in determining whether a query matches the pattern. Finally, in the third example, we have queries as data science, deep sea, dolphin search, and the pattern is DS. The output is true, false, false. Here, data science matches because the uppercase letters D and S appear in the correct order, and we can insert lowercase letters to form the query. However, deep sea does not match because the uppercase letters in the query do not follow the required order of the pattern. Similarly, dolphin search does not match because it contains an extra uppercase letter that is not part of the pattern. The constraints of the problem also highlight important edge cases, such as when queries are shorter than the pattern, when queries contain extra uppercase letters, or when the match happens without needing any lowercase insertions. This ensures that the solution handles a wide range of scenarios effectively. To solve the Camelcase matching problem, we need to determine if each query in the list matches a given pattern based on Camelcase rules. Here's how this works. A query matches the pattern if we can add lowercase letters to the pattern to form the query, while keeping the order of uppercase letters intact. For instance, with the pattern FOBA, the query foobar is valid because we can transform FOBA into foobar by adding lowercase letters. However, foobar test does not match because it contains an extra uppercase letter, T, which is not part of the pattern. The key here is that the pattern dictates both the sequence and case of uppercase letters. This means that a valid query must preserve the order of uppercase letters from the pattern, and it cannot introduce additional uppercase letters. Essentially, we can think of the problem as checking whether the pattern is a subsequence of the query, with the additional constraint of ensuring no invalid uppercase letters appear in the query. One way to approach this problem is through a brute force method. Here's how it works. For each query in the list, we check if the pattern is a subsequence of the query while validating the uppercase letter constraints. To do this, we use two pointers, one for the pattern and one for the query. As we traverse the query, we compare each character with the current character in the pattern. If they match, we move the pattern pointer forward. If we encounter an uppercase letter that does not match the pattern, we immediately return false for that query. If the pattern pointer reaches the end of the pattern during this process, the query is valid. Otherwise, it is not. The time complexity of this approach is O(n*(m), where n is the number of queries and m is the average length of each query. It requires no extra space, making the space complexity O(1). However, this method has drawbacks. It can be inefficient for large input sizes due to repeated traversals and does not take advantage of opportunities for early termination when mismatches are detected. To improve on the brute force approach, we can use an optimized two-pointer method. This strategy retains the same fundamental idea of comparing the pattern and query using two pointers but introduces early termination to enhance efficiency. Specifically, as we traverse the query, if we encounter an invalid uppercase letter or determine that the pattern cannot match any further, we immediately stop processing that query. Additionally, we ensure that by the end of the traversal, all characters in the pattern have been matched, and any remaining characters in the query must be lowercase. This approach includes key enhancements, such as validating uppercase letters during the traversal itself and exiting as soon as mismatches or violations occur. While the theoretical time complexity remains O(n*(m), the number of operations per query is reduced, making this method faster in practice. Like the brute force method, it uses O(1) additional space. The optimized two-pointer approach offers several advantages. It is generally faster in real-world scenarios because it reduces unnecessary computations through early termination. It is also simpler to implement compared to more advanced alternatives. This makes it our chosen strategy for solving this problem. We selected this method because it strikes a balance between simplicity and efficiency. It avoids redundant calculations and provides better performance without adding unnecessary complexity. While other approaches, like regex-based solutions or dynamic programming, are possible, they come with trade-offs. Regex solutions are harder to read and debug, while dynamic programming approaches, though powerful, are unnecessarily complex for the constraints of this problem. The two-pointer method is both practical and effective, making it the most suitable choice. In conclusion, the two-pointer method is the ideal solution for the Camelcase matching problem. It efficiently handles the requirements of the problem while maintaining clarity and ease of implementation. By leveraging early termination and minimizing redundant computations, this approach strikes the right balance between performance and simplicity. It avoids the pitfalls of more complex alternatives, making it the most practical choice for solving this problem effectively. To solve the Camelcase matching problem, we start by carefully parsing the input. We're given two key components: a list of queries, where each query is a string, and a pattern string that serves as the template we need to match against using Camelcase rules. The objective is to determine if each query aligns with the Camelcase structure defined by the pattern. For each query, we aim to return a Boolean value, true if it matches, false if it doesn't. Next, we define the rules for a valid match. First, all uppercase letters in the pattern must appear in the same order within the query. This ensures the structure of the pattern is preserved. Second, any extra lowercase letters in the query are acceptable, but they cannot interfere with the sequence of uppercase letters from the pattern. Finally, the approach involves iterating over each query and checking if it satisfies these conditions, which we'll break down step by step. We begin the matching process by using two pointers to traverse the pattern and the query simultaneously. Pointer I tracks the position in the pattern, while pointer j does the same for the query, and both start at the beginning. As we iterate through the query, several scenarios are handled. If the current character in the query matches the character in the pattern pointed to by I, we increment both pointers to proceed to the next characters. If the current query character is a lowercase letter not part of the pattern, we simply increment j to skip it, as extra lowercase letters are permitted. However, if the current query character is an uppercase letter that does not match the pattern at I, this violates the Camelcase rules, so we terminate and return false immediately. After processing the query, we check if there are unmatched characters remaining in the pattern. If I has not reached the end of the pattern, it means not all pattern characters were accounted for, and we return false. Otherwise, if all conditions are met, we return true for the query. With the matching logic implemented, we now need to store the results for all queries. For each query processed, we collect the outcome, true or false, into a results list. At the end of the process, this list is returned as our final output.
There are some important insights to keep in mind about this algorithm.
First, Camelcase matching is highly order-sensitive, meaning the sequence of uppercase letters in the pattern must strictly follow their respective order in the query.
For example, a query like FO bar matches a pattern FB, but bar FO does not. Second, lowercase letters in the query offer flexibility, they can be ignored unless they disrupt the uppercase order. This allows queries like foobar test to match FB, but not foo test bar, where the order is broken. Finally, the algorithm allows for early termination. If an uppercase mismatch occurs, we can stop processing the query immediately, which improves efficiency. The algorithm relies on specific data structures for efficient implementation. The two-pointer approach is key for traversing the query and pattern in a single pass, ensuring that the matching process operates in linear time relative to the length of the query. The result list is another essential structure, used to store the Boolean outcomes for each query, which are appended as we process them. There are also three critical operations. First, character matching ensures that the uppercase sequence in the query aligns with the pattern. Second, skipping extra lowercase characters in the query allows the algorithm to handle non-pattern characters gracefully. These operations ensure correctness and efficiency while adhering to the Camelcase rules.
Efficiency is a major strength of this algorithm, and we can analyze it in terms of time and space complexity.
For time complexity, each query is processed in linear time relative to its length.
If the average length of the queries is m and there are n queries, the total time complexity is O(n*(m).
This is because each query is traversed at most once thanks to the two-pointer approach.
For space complexity, the algorithm uses minimal additional memory, primarily for the two pointers and the results list. The space complexity is O(n), where n is the number of queries, as that's the size of the output list. This makes the solution both time and space efficient, ensuring it scales well even with larger inputs. This solution implements the CamelMatch function to determine if each query string in the queries list matches the pattern based on Camelcase rules.
Here's a step-by-step breakdown.
1. We define a helper function isMatch that takes two strings, query and pattern, and checks if the query matches the pattern using Camelcase rules.
2. Inside isMatch, we use two pointers, I for traversing the query and j for the pattern.
Both start at index 0. 3. We iterate through the query while both pointers are within their respective string bounds.
For each character, if the current characters of query and pattern match, we move both pointers forward. If they don't match and the current query character is uppercase, the query is invalid since it introduces an extra uppercase letter that is not part of the pattern. In this case, we return false. Otherwise, we simply move the query pointer forward. After exiting the loop, we check if there are any remaining uppercase letters in the query.
If found, we return false as this violates the Camelcase matching rule. 5. Finally, we verify that the pattern pointer, j, has reached the end of the pattern.
This ensures all pattern characters are matched in the query.
6. The CamelMatch function applies the isMatch helper to each query in the queries list and returns a list of Boolean results.
Each result indicates whether the corresponding query matches the pattern.
This implementation is efficient and handles edge cases, such as empty queries, patterns, or additional uppercase letters in the queries, correctly. The algorithm operates in O(n*(m), where n is the number of queries and m is the average length of the queries or the pattern. In this Java implementation, we start by defining the CamelMatch method, which takes an array of query strings and a pattern string as input.
The goal is to determine whether each query matches the given pattern based on Camelcase rules.
To do this, we initialize a list Boolean called result that will store the matching outcomes for each query. Then, for each string in the queries array, we call the helper method isMatch, passing the current query and the pattern as arguments. The result of this helper method is added to the result list.
Next, we move to the isMatch method, which performs the actual comparison.
Here, we use two pointers, I and j, to traverse the query and pattern strings respectively.
The logic starts by iterating through both strings while ensuring neither pointer exceeds its respective length. If the current characters from query and pattern match, we increment the j pointer to move to the next character in the pattern.
However, if the character in the query is uppercase and does not match the current character in the pattern, the method immediately returns false, as this violates the Camelcase matching rule. The I pointer is increment in each iteration to continue processing the query string.
After exiting the main while loop, we perform a final check for any remaining characters in the query string. If there are uppercase characters left, the method returns false, since these characters would conflict with the pattern's Camelcase structure. Otherwise, we verify whether the pointer j has reached the end of the pattern string. This ensures that all characters in the pattern have been matched successfully. If this condition is met, the method returns true. Overall, this implementation combines pointer-based traversal and character checks to efficiently determine whether each query adheres to the Camelcase format defined by the pattern. In the Camelcase matching problem, we are tasked with determining whether a given pattern matches each query in a list of queries according to Camelcase rules. Specifically, for a query to match the pattern, the characters in the pattern must appear in the same order within the query. Additionally, any extra uppercase letters in the query must correspond to characters in the pattern. Our output is a list of booleans where each boolean indicates whether a particular query matches the pattern. For example, consider the input queries foobar, test, and football with the pattern foba. To solve this, we define a helper function called isMatch that checks each query against the pattern step by step. Starting with the first query, foobar, and the pattern foba, we initialize indices I and j to 0, which represent the current positions in the query and pattern respectively. We compare the first character of the query, f, with the first character of the pattern, also f, and find a match. Both indices are increment. Next, O in the query matches O in the pattern, so we increment both indices again. The next character, O in the query, does not match B in the pattern, but since O is lowercase, we simply skip it by incrementing the query index. Continuing, B matches B, and A matches A, incrementing both indices each time. At the end of the pattern, we verify that the remaining query contains no uppercase letters, confirming a match and returning true. For the second query, foobar test, the steps are similar up to the end of the pattern. However, the remaining part of the query, test, contains an uppercase letter T, which disqualifies it. Therefore, we return false. Now, let's analyze the third query, football, with the same pattern, foba. Starting with the first characters, f matches f, and o matches o, so we increment both indices. However, the next o in the query does not match b in the pattern, so we skip it by advancing the query index. The same happens with t, which is also skipped. When we reach b in the query, it matches b in the pattern, and a matches a, completing our traversal of the pattern. At this point, the remaining part of the query, ll, contains no uppercase letters, so this query is a match, and we return true. Combining the results for all three queries, the output is true, false, true. In another example, we use the queries coding by, code block, and camelback with the pattern CB. For the first query, coding by, the characters C and B in the pattern are found in sequence in the query. After matching the pattern, we ensure that no extra uppercase letters remain in the query, so it is a match, and we return true. For the second query, code block, the same process applies. Both C and B are matched sequentially, and no disqualifying uppercase letters remain, so this query also returns true. Finally, for camelback, we again match C and B in order, and the rest of the query contains no extra uppercase letters, resulting in true. The final output for this set of queries is true, true, true. Throughout the solution, we track the indices I and j to ensure that the characters in the query match the pattern sequentially. This approach ensures that the order of the pattern is preserved within the query. Additionally, we verify that any extra uppercase letters in the query, which do not align with the pattern, disqualify the query. The helper function isMatch encapsulates this logic, allowing us to process each query efficiently. The output is a Boolean list, clearly indicating which queries satisfy the Camelcase matching rules for the given pattern. To determine the time complexity of this solution, we start by analyzing how it processes the queries list and matches them against the pattern. Let's define n as the number of queries, m as the average length of the queries, and p as the length of the pattern. The function iterates through each of the n queries, which means the outer loop makes n calls to the isMatch function. Now, within the isMatch function, two pointers are used, one for the query and another for the pattern. These pointers allow for a linear scan of the query,
ensuring that each character is checked exactly once. In the worst case, this traversal takes O, max, M, P, time for a single query, as it accounts for both matching the characters of the query with the pattern and verifying any remaining uppercase characters in the query. When we combine this with the outer loop that processes all N queries, the overall time complexity becomes O, N asterisk max, M, P. This reflects how the solution scales with the number and length of the queries, as well as the length of the pattern. Now, let's break this complexity down further to understand the best, average, and worst case scenarios. In the best case, the queries are either very short or mismatches occur early during comparison. This minimizes the number of characters processed per query, reducing the time complexity per query to approximately O(p). For N queries, this results in a total time complexity of O, N asterisk P. On the other hand, the worst case occurs when each query is long, nearly equal to M, and requires a full scan to determine if it matches the pattern. Here, the total complexity remains at O, N asterisk max, M, P. Shifting to space complexity, the solution only uses a constant amount of auxiliary space within the isMatch function. This is because it relies on two integer pointers, I and j, without any additional data structures, leading to an O(1) auxiliary space complexity. The output space, however, contributes O(n) as we store the results for all N queries in a list of booleans. When we combine the auxiliary space and the output space, the overall space complexity of the solution is O(n). To appreciate the efficiency of this solution, let's compare it to a brute force approach.
A naive method might generate all possible subsequences of each query and check if any of them match the pattern.
Since a query of length m has 2 to the power of m subsequences, this approach would require exponential time O(2 to the power of m) for a single query. For n queries, the total complexity balloons to O(n asterisk 2 to the power of m), which is computationally infeasible for larger inputs.
In contrast, the optimized solution avoids this inefficiency by using a two-pointer traversal to directly compare each query with the pattern.
This method processes each query in linear time relative to its length, reducing the total complexity to O(n asterisk max, m, p). Mathematically, the linear scan guarantees that every character in a query is evaluated at most once. Given n queries and a maximum query length m, this results in a worst-case operation count proportional to n asterisk m, which aligns with the O(n asterisk max, m, p) time complexity. Meanwhile, the space complexity remains dominated by the output list of size n, confirming the O(n) space usage. This comparison highlights the significant performance advantage of the optimized solution over a brute force approach.
When tackling Camelcase matching, there are several common mistakes to watch out for. First, remember that this is a case-sensitive problem. Uppercase and lowercase letters are not interchangeable, so your algorithm must explicitly account for this distinction.
Ignoring case sensitivity will lead to incorrect results. Next, ensure that characters in the pattern are matched in strict order. The pattern cannot have characters skipped or rearranged during matching.
Another frequent error involves ignoring extra uppercase letters in the query.
If a query contains uppercase letters that do not correspond to any uppercase letter in the pattern, it cannot be considered a match. Finally, be mindful of inefficient string traversal. Traversing the query or pattern multiple times unnecessarily increases the time complexity of your solution. A single pass traversal of both strings is ideal for achieving efficiency in your implementation. Edge cases are another critical area to address, as overlooking them can introduce bugs.
Examples include scenarios with empty queries, empty patterns, or queries that are entirely lowercase or entirely uppercase. These situations must be explicitly handled in your logic. From an interview perspective, it's important to fully understand the problem scope. Interviewers may ask for variations, such as case-insensitive matching or incorporating wildcards, so being adaptable is key. Optimization is also highly valued.
While a brute force approach might work for small inputs, it won't scale for larger constraints. Strive for a solution with O(n plus m) complexity, where n and m are the lengths of the query and pattern. Additionally, testing your solution on a diverse set of cases, including both short and long strings as well as edge cases, ensures robustness. Finally, during interviews, communicating your thought process clearly, especially how you handle each character in the query and pattern, can help demonstrate your problem-solving approach effectively. Expanding on this topic, there are several related problems that can provide valuable practice and insights. For example, LeetCode 10, which focuses on regular expression matching, involves pattern matching with wildcards and often requires a dynamic programming approach. Similarly, LeetCode 44 explores wildcard matching, though its rules for wildcards are simpler than regex. Another useful problem is LeetCode 791, where you implement custom sorting of strings based on specific rules, emphasizing string manipulation. Finally, LeetCode 1451 challenges you to rearrange words in a sentence under certain constraints, highlighting the importance of sorting and string manipulation. These problems build foundational skills that complement your understanding of Camelcase matching and help you tackle variations more confidently. To approach Camelcase matching, there are several alternative techniques you can consider. One efficient method is the two-pointer technique, where you use one pointer for the query and another for the pattern, traversing both simultaneously. This approach ensures linear time complexity and is a practical choice for many scenarios, though it might feel less intuitive for beginners. Another option is a regex-based approach, where you construct a regular expression from the pattern to perform the matching. While this method can simplify the logic and lead to concise code, it tends to be less efficient and may struggle with scalability for larger inputs. Lastly, a more advanced technique is the state machine approach. By designing a finite state machine, you can handle even more complex matching scenarios. However, this method requires additional effort to design and debug, making it less common in typical interviews but potentially valuable for production-level systems. Great job! Today, we tackled the Camelcase matching problem and learned about handling string patterns effectively. We discussed key insights and approaches to solve this type of problem efficiently. Keep practicing, and don't forget to check out other related problems. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!